Hello students, this is Mr. Bornhammer and we are going to today look at a force problem for general physics. So let's take a look. A 5 Newton box is being pushed up a rough ramp that is 25 degrees above the horizontal. The box is being pushed up at a constant velocity with a force of 25 newtons. And what we're trying to identify here is what is going to be the F net in the X direction, what is going to be the F net in the Y direction, and when all combined, what is the magnitude of F net total on this object, being the box. Well, the first thing that we have to kind of note here in this problem, and it's actually very important, is this constant velocity. Okay, everything we've been talking about up to this point has been centered around, displacement, distance, velocity, initial, final, acceleration, and now we're going to be talking about force. And one of the things that is crucial to understanding force is that a force is a push or pull, and a force causes objects to accelerate. All right, now, if you have a constant velocity, that means that after you've looked at all of the forces acting on an object, that object would basically have to have zero acceleration. And if it has zero acceleration, then the F net magnitude, when everything is all said and done, has to be zero. So in some ways, we can solve this whole problem by saying the F net magnitude for this problem is going to be zero, because those words, constant velocity, means zero acceleration. Acceleration can only happen if an object is speeding up, slowing down, or changing direction. So this box is moving in a straight line. It's not speeding up, it's not slowing down, so it has no acceleration. And force is defined as an object with mass that's accelerating, that's either being pushed or pulled by either contact or field forces. So this box can't have F net that is anything other than 0 newtons. Okay, now to figure out F net in the X direction and F net in the Y direction, okay, in order for this to be 0, in theory, these would also have to be 0. But I will tell you, unless you can explain why these are 0, you are not doing yourself any favors, okay? So let's just quickly look at why everything is 0. So I'm going to go ahead and I'm going to draw our ramp like so. And this ramp is definitely not to scale. It only should have a 25-degree incline. So while that is considerably larger than 25 degrees, I'm still going to write 25 degrees in here. And we're going to draw our little box on this ramp, like so. Now, there are several forces that are definitely acting down on this box right now. Like we've talked before, there's the force of gravity that is pulling this down, and your equation sheet calls that FW. Okay, so I'm going to try to use the same notation. There's also the normal force, which is acting outward. Okay, so we're going to call that FN, like so. We've been told that the motion of the box is in the upward direction, so I'm just going to go ahead and put an arrow here, and we're going to call this motion, or we can even call it direction of motion, like so. So I have the direction of motion, my normal force, the force of gravity, okay, and I have my 25-degree incline. Now, when we are talking in a problem about using X and Y, Okay, so let me kind of scoot this down a little bit. X and Y, those have to be defined. And in a problem that is slanted like this, that is a very hard thing to do. So one of the things you have to do is you have to define X and Y coordinates. So typically speaking, when you have a slanted surface, and we kind of briefly discussed this, we're going to call this slanted axis, we're going to call that X. Kind of think of it as if that was flat, and it's not, but think of it if it was. Okay, if that was like a flat, okay, then this would be perpendicular. Notice it's right along that normal force. Okay, and I'm going to call that Y. Now, let's turn it back to reality. And so really all I've done is I've taken the X axes and the Y axes, which are indeed perpendicular to each other, and I have just taken them from what they would normally be like this and rotated them slightly. I've actually rotated them 25 degrees. Okay, so in theory, because I've rotated them 25 degrees, this angle here is also going to be 25 degrees. If they were here normally and they were rotated 25 degrees, they're now like that. All right, now this rotation, okay, allows us to use the normal force, which is along Y. So your F net Y up here, that's going to include the normal force, okay, because the normal force right here is acting along the Y axis, which I have defined. But gravity is tricky, okay? Gravity, let's take a closer look here. Gravity is not playing very nice. All right, and the reason for that is because it doesn't fall along our axes. And that's a very, very tricky situation to be in. All right, because it doesn't fall along our axes, X here or Y here, you're going to have to break it up into its horizontal and vertical components. So let's zoom back out here a little bit, like so. So I've gone through the liberty of doing this on a separate sheet of paper. Okay, so let's just kind of go through this briefly real quick. Let's say this is our force of gravity here, okay, and this would be along the Y here, and this is along the X here. And if I even just set it off to the side here so you can see it, FW, FW, this part of FW, which would be along the Y, and this part of FW, which is along the X, okay, like right here. And so what ends up happening is, and if you want to just pause this video and kind of look at it, I'd highly recommend it. What ends up happening is if you were to use your trigonometry, okay, you would see that the FWX, which is this value here, is really the hypotenuse, FW, times the sine of 25 degrees, or the sine of theta. And this adjacent side, okay, is going to be FW cosine theta, like so. Now, using that information, I can go ahead and draw it all in. So I would say that, okay, the part of FW here would be really FW in the Y direction. So I'm going to go up to the top. I'm going to say, okay, and it's kind of focusing like crazy here. Let's let it try to refocus. Perfect. And let's go ahead and lock the focus. All right, the normal force is in the Y direction, and there's a part of gravity that's in the Y direction. There's also that part of gravity that's in the X direction, or the horizontal direction. So we will come back up here, and we will say that the FW X is also in the X direction. Now, in the problem it tells us that they're pushing with a force of 25 newtons. So we have to assume for just a moment that there's a force that's pushing the block up the ramp. We're going to call it the force of push. And we're going to have to assume that that force of push is 25 newtons. Now, it's up the x-axis here. So we're going to call this the force push. And last but not least, there would also be a little bit of resistance due to friction. And actually, because this is a rough surface, friction always opposes motion. So it's going to be actually pointed down because the motion is up. So there'd be friction along the x-axis as well. And so I would come back up here and I would say that in the x direction, there's the force of friction. So if I were to take the force of gravity in the x direction, which is this one, the force push, which is this one, and the force of friction, which is this one, and I were to add them all up, these two forces would add up to a negative 25, and the force push would add up to a positive 25, and so this x direction would be 25 minus 25, which is 0. The y direction is trickier. The normal force is opposing this component of gravity, and they would be equal and opposite. Okay, and if you wanted to actually do the calculations, you could. Okay, and I believe it works out to be like a positive and negative 4.53 newtons. But when you add them two together, because they're equal and opposite, they'll cancel each other out. And so again, the normal force and the force of gravity in the y direction here would add up to 0 newtons as well. So really, this problem is actually quite easy. There's not a whole lot of math to it. If you needed to explain it, we could do all of that. But really, these two words, constant velocity in the problem, constant velocity, basically tell us that the net magnitude has to be 0 because there's no acceleration. And if that's the case, then when you add up all of the x vectors, okay, so Fwx, the force push, the force of friction, they all cancel each other out. And when you add up all the y vectors, the normal force and the force of gravity acting opposite the normal force, they also cancel each other out. And so really this problem ends up being 0 newtons, 0 newtons, 0 newtons. Okay. If you have any further questions about this problem or you'd like to see more specifically the math, please let me know. Otherwise, thanks for watching.